mathematics. It will be a little too much of me to chair such sessions of mathematicians, being an engineer. But still, when Professor GB told me that essentially the subject is mathematicians of Kerala, I thought that it will be okay. Of course, it will be okay for me to perhaps listen, as also generate a few questions and also ask a few questions. Of course, I have known Professor Krishnachandran sir from a long time back, while he was he was a professor at GEC Thrissur. In fact, I have heard of his fame. And my daughter, being a mathematician, was also attracted to whatever he was in that sense. Later on, he became the principal of Government College Victoria also. So he has both experience as an excellent teacher. In fact, I have listened to several sessions of his, so I know that he's an excellent teacher. I also have experienced the way in which he offers sessions. They are exemplary. In fact, we have a lot to learn from the manner in which he offers sessions. And as an administrator also, he has rich experience, which we could actually encourage in Vidya. When I became the principal, in fact, I had asked for a vice principal, and it was none other than Dr. Krishnachandran sir. So moving on to his interests, though he has published a large number of research papers, which was talked about in the morning, and he has written a few books. In fact, I have seen two of his books at least, and I've also understood that he dabbles in what he calls as computer algebra, where certain sessions were offered to many of us. In fact, I have attended two of them. Then again, I noticed that he is interested in Wikipedia to the extent of improving upon the content, which again is a pastime. According to him, it's a pastime. He has now recently dabbled in another pastime when he has created many, what do you call them, apps. Okay, many apps of importance, starting with our college, our own college diary as an app. Then again, it's called as Vidya Mobile. Then we had the Ramayana coming out, and recently then we had I suppose I forget the chronology. Anyway, we had at least 3 important apps coming from his table. Of course, he was the leader, and of course, he might have taken the help of the department people also. So we are very proud to have him here, and it speaks a lot for his capability, as also his humility, when he agreed to step in when we lost one of our speakers from Italy due to technical reasons. So he agreed, I believe he agreed yesterday, and today he's ready to speak to us. So welcome Professor Dr. Krishnachandran sir to the session. Let's hope that we'll all enjoy a very happy session with him, because he says happy learning. So let's all do happy learning. Thank you, sir.
Okay, thank you so much for all the kind words. Dear participants, the organizers, and others attending this session. I always felt that in any conference in Kerala, there should be at least one session devoted to Kerala mathematics. One reason is that, the main reason is that the contributions of mathematicians in Kerala are not still widely known. Historians of mathematics have acknowledged these contributions as of priceless value, and other scholars are now aware of that. But my feeling is that those names have not become household names. That is one of my dreams, actually. Everybody knows about Newton. Your mothers and the grandmothers will also be knowing about Newton or Einstein. They have heard of those names. They may not know what are their contributions. They know those names. But if you ask, say, our fathers or your sisters or anybody, what was the greatest mathematician in Kerala? I am afraid nobody will be able to just say that name. The contributions of Kerala mathematicians are comparable to, at least in some certain aspects, comparable to the mathematics of Newton. Some of the discoveries that happened in Kerala happened at least 2 centuries before they were discovered in the European continent. You must be really proud of that. I lose no chance talking about that. Even if you are not interested, I will try to make you interested. That is what I feel. So even though what I am going to talk about is not much relevant to the theme of the conference, in some sense it is relevant, because all the mathematics developed in India, they were all applied mathematics. Mathematics, there was no distinction between pure and applied mathematics. They just talked about Ganitam, and it was only applied mathematics that they talked about. They talked about the applications of mathematics in astronomy. So Ganitam was actually a part of astronomy. So in that sense, the mathematics that developed in India and then when they were discovered and studied can definitely be called something like an applied mathematics. Okay, I was told about this necessity of having a class today, yesterday or day before yesterday. So within 2 days I have to prepare the slides. So I did not, I'm not sure whether I have done it the way I wanted it to. I hope you will enjoy those things. Now the title that I have chosen is the contemporaneousness of medieval Kerala mathematics. Contemporaneousness. Why it is contemporary? What is generally talked about when somebody talks about Kerala mathematics is the full mathematical aspect. The discovery of the series expansion for sin x, series expansions for cos x, then series expansion for tan x, tan inverse x, and things like that. And these are the points that are generally stressed. So I thought I will say something different, something perhaps new, which are not seen in books. In fact, these findings I myself have presented in some conference about a decade ago, but those ideas have not yet found a place in any other references. So some of the ideas that I am going to present are, I think, new, not mentioned in, to my knowledge, at least to my knowledge, not seen mentioned in any of the publications. So that is the contemporaneousness aspect that I wanted to talk about. Okay, so I have divided my talk into 2-3 parts. In the first part, I will say something about the Kerala mathematicians, and the second part, I will say what was the main contribution of the Kerala mathematicians, and in the third part, I will say what are the contemporaneousness of these results. So that is how the talk is arranged. I hope I'll be able to cover those areas in the short time. All of you will be able to understand what I am talking about, because it is the mathematics that I am talking about is at the level of a degree student or a degree student, BSc. Even engineering BTech students can also understand what I am talking about. +2 students may not be able to. And remember, these mathematics were the mathematics that was studied 2 centuries before Newton. Imagine somebody coming in a loin cloth, വായിൽ നിറയെ മുറുക്കാനുമായി വന്ന് സയൻസീസിനെ കുറിച്ച് ക്ലാസ് എടുക്കുന്ന ഒരു പ്രൊഫസറെ കുറിച്ച് ആലോചിക്കുക. അതാണ് കേരള മാത്തമാറ്റീഷ്യനെ കുറിച്ചുള്ള ഒരു ചിത്രം. Okay, I am sorry if I change to my local language. I am sure there are a few people who are... Okay, so let me now move over to the slides, and I will explain the ideas with the help of those slides. So let me move over to the slides, please. Okay, I hope you can see. You can see the slides?
Yes, sir.
Okay.
Yes, sir. Clear. Slides are clear.
Okay. Okay, so that is only the opening slide, and that is also contains the details, so that also is skill. And this is the outline that I have mentioned. Okay, I will also say I'll show one or two slides about the classical period in mathematics. So regarding the classical period in Indian mathematics, is generally considered to have begun with Aryabhatta. Okay, even before Aryabhatta, there was mathematics. There was what has been referred to as Vedic mathematics, even though Vedic mathematics is neither Vedic nor mathematics. But there is some mathematics in Vedas, and there are mathematics in the as part of the Upanishads or some other works. But there are pre-classical period. The classical period begins with the Aryabhatta. And these are some of the mathematicians of the classical period. Most of you will be familiar with these names because these are all included in our textbooks. And all our textbooks start with Bhaskara 2, the author of Leelavadi. I think that is the last reference that we study in schools and colleges. Bhaskara 2 ends there, as if nothing happened after that. But here what I am trying to say is that many things happen after that, and that happened in Kerala. So development of mathematics in India did not end with the Bhaskara 2. I say like this because I have not seen current textbooks. I'm not very familiar with what is being taught in the schools and colleges nowadays. But quite recently, about 10-20 years ago at least, there was no reference to any mathematics that is being developed in Kerala. So it is in this context that I say development of mathematics in India did not end with the Bhaskara 2. Okay, so I'll say something about the Kerala School of Mathematics. That school, that their history can be divided into. So before that, okay, before saying that history, it's a very interesting historical incident. As I mentioned in the previous slide, this is not generally known. Interestingly, an East India Company official by name C.M. Vish has published a paper on this in 1832. 1832. Okay, I can show you the title of that paper. This is actually a facsimile of the paper that he published in 1832. It's published in the Transactions of Royal Asiatic Society of Great Britain and Ireland. See on the Hindu, just read the first 2 lines. On the Hindu quadrature of the circle and the infinite series of proportions of the circumference to the diameter, exhibited the 4 Shastras, the Tantra Sangraham, that is the name of one book, Yukti Bhasha, that is again another book. We will see that in detail later. It is Karana Bhattadi. C stands for K. At that time, K was transliterated as C. So it is not Charana Bhattadi, it is Karana Bhattadi, then Sadratnamala, etc. by Vish. So even though it was published as early as 1832, but nobody took notice of that. It was completely forgotten. It was completely forgotten, and
ഒരു സർവകാലയില്ലേ എല്ലാവരും ഒരുപാട്.
Okay, it is completely forgotten, and that came to light only in the second half of the last century. Now, the geographical location of the Kerala school, that is also very, very interesting. That to say a small area in current in the Malappuram district is around Thrissur in Malappuram district. Thrissur, Thrikkandiyur is the area where all the mathematicians lived. Interestingly, see, I think there was a very great revival of learning at that time. The Tunjat Ramanujan Acharyan, Melpattur Narayana Bhattacharya, and such scholars flourished more or less during the same period. Perhaps there was a great revival of learning. Something like a renaissance was happening during that period in that small area. Okay, so the next slide shows this little square represents the area where these mathematicians flourished. Okay, okay, I hope you can see that. Thrikkandiyur, period can be actually divided into 3 periods. The defining person is this Madhava. I will tell you more about Madhava the next slide. So pre-Madhava, then Madhava and its disciples, and post-Madhava. So the history of the Kerala School of Mathematics can be divided into 3 periods like this. Okay, I told you that I am going to say something more about Madhava. Unfortunately, nothing more can be said. Only very little details are known about the life and work of Madhava. Only one book of Madhava has survived. All other data is obtained from the writings of later mathematicians. Oh, okay. This is also interesting. See, this is an image of Sangama Madhava. He was referred to as Sangamagrama Madhava. This image, I think it was constructed very recently, about 10 years ago. It was constructed by studying the features of people who are supposed to be his descendants. Supposed to be his descendants. This image was constructed. So there was, it's not actually the real image of Madhava. It's constructed based on the physical features of people who are considered to be the descendants of Sangamagrama Madhava. Okay. So as I just mentioned, these dates, now look at the dates, 1350 to 1425, Common Era. Dates are uncertain. There is no way in which, by which these days can be ascertained. It's around that period, that's all we can say. No personal details about Madhava has come to light. Now the name is referred to, later authors always refer to him as the Sangamagrama Madhava. Sangamagrama Madhava. Some people have identified Sangamagrama as Irinalakuda in Thrissur district, because the Pradishta, the deity in the Irinalakuda Kodalmanikan temple, is sometimes referred to as the Sangameshwaran, and so the grama of the village of the Sangameshwaran is a Sangamagrama. That is sometimes called Sangamagrama, and so it is believed that he was a native of Irinalakuda. And there are some references to him in the works of the other authors, about whom accurate details are available. So from these references, these dates have been established. And we know his contributions from the later works. Okay, some other prominent mathematicians of the school were Parameshwara, a pupil of Sangramagram Madhava. He is the promulgator of the Drirganita system of astronomical computations. The Drirganita system, that is the system that is now being followed by those who compute the Panchang and published by the various agencies. Madhurami Panchang is there, Manorama Panchang is there, and the Guruvayur Devasam Panchang is there. So these people do the calculations based on the Drirganita system. Parameshwara is said to have observed the skies for about 50 years. And he recorded his observations, and he saw that the recorded observations are at variance from the predicted values as per the previous computations. So based on he interpolated, he calculated back and introduced corrections to these constants, and the new system is called Drirganita. So Parameshwara is the author of the Drirganita system, and another prominent person was called Damodara. Then another very important person of that period was Nilakantha Somayaji. Again, exact details are available. He lived for 100 years, 1454 to 1544. He is a pupil of Parameshwara, and his work is a very famous work is Tantra Sangraha. Is completed in 1501. That book has been translated, and the complete details are now available. Is available in Springer. Now, another important mathematician of that period is Jyeshtha Deva. Jyeshtha Deva, who lived, again, only approximate days are available, during 1500 to 1575. He has written a book called Yukri Bhasha. All of you must know the name. Yukri Bhasha. Ganita Yukri Bhasha is a commentary in Malayalam. In Malayalam of Tantra Sangraha by Nilakantha Somayaji. Commentary on Tantra Sangraha in Malayalam. Now see, some interesting things are, okay, this is again, that book has been published. I have a copy of that book. It is the translated book. It is divided into 2 volumes. In one volume, the author deals with mathematics. In the second volume, the author deals with astronomy. So the English translation has, again, 3. Each volume has 3 parts. First, the full text in Malayalam, then its interpretations in modern mathematical notations, and the third part is a literal translation into English. So in this way, that book has been organized into the 3 parts, and there are 2 volumes, each volume containing 3 parts. The book is entirely in Malayalam. It's something surprising. Okay, so what is the use of that? What is the use of that? It means, see, our language is so powerful. The vernacular, our language is so powerful that, see, it can express even the finest thoughts, finest ideas in mathematics. It contains the statements of the power series expansions with sine and cosine functions, and also their proofs in Malayalam. In Malayalam. So that should make all of us who live in this part of the country, at least all Indians, not only people in Kerala, all people in the in India must be proud of that. Our regional languages are so powerful. So why should we depend on other languages? Of course, okay, and currently, of course, we may require English language, but let us not look down upon our mother tongue. Here is proof about the capability of our mother tongue. And another point that is worth stressing, see, if you read the writings of some of the Western mathematicians, Western historians of mathematics, they disdain Indian mathematics. They just make an accusation that all our mathematical texts contain only the results, and they accuse us lacking a sense of proof. We are not bothered about proof; we are only bothered about results. In fact, that idea has been disproved because that book contains proofs of all the statements. Proofs of all the statements. So this point, all of us must be, okay, I'm sorry, all of us must be aware of that. Okay, then there are some later mathematicians, so that does not end with Yashtadeva. The tradition continued, and perhaps the last known person in that lineage is the person last named Shankaravarman, is the author of Satyaratnamala. The Pudumaya Soyaji has also written a book called Karanabadhati that has also been translated, and that is also available in the market. Okay. Yes. Now, I'll just say briefly what are the mathematical achievements of Kerala school. I say I'm not going to, this is a deep topic to explain all the mathematical achievements of Kerala school. So that I'm not going to do. What I am going to do is just point out one thing, the sign series expansion. That's all. So this diagram will explain the terminology used by the mathematicians of India and the mathematicians of Kerala. Okay, let me just, okay. The arc is called Chapa. The Jia, it is called Jia or Jiva. Jiva is that vertical altitude. Is Jia or Jiva is similar to our cosine. This is the sign of that Chapa. Sign of the Chapa is the arc. So sign of the arc means sign of the angle submitting the center. The arc is defined by the angle submitted at the center. So Jia here is the sign of the Chapa, and in the bottom line Kodijya or Kojya. Kojya is that small part, that is the cosine of the arc. In fact, the word sine comes from Jya, and the word cosine comes from Kojya. Cos comes from Kojya. Then the other half is called Utkramadjya, and see, just be familiar with this terminology. Okay, that's all. Now, these are expressed in modern notations here. Jia of arc AB, F arc AB, RKB, F arc AB, that is BM. BM is R sine S by R. When I say S by R, we need the angle theta. S by R is the angle theta in radians. So BM is R into R sine S by R. Kodijya is OM R cos S by R. So mathematicians in Kerala were trying to get values of this Jya and Kodijya, not to sine and cosine as such. And that is why I have shown these examples. Now that is again an interesting thing. The values are represented in a certain scheme known as a Katapayadi scheme. Katapayadi scheme is a method of representing numbers using letters of the Sanskrit alphabet. That scheme is shown in the next slide. the letters, the first column, ka, it is ta, it is not ta, ta, pa, ya. That is why it is called katapaya. All those represent the number 1. The next ka, ta, pa, then ra. Those represent the digit 2, like that. So this scheme is known as the Katapayadi scheme. Incidentally, this scheme is used to represent in music also, in Carnatic music also, this system is used. Now,
sorry to interrupt you, sir. We have 10 more minutes.
Okay, I'll finish within 10 minutes.
Okay, thank you, sir.
Okay, I'm aware. Okay, now the way in which these letters are translated into digits. All the details are given, but the details are not very, very significant. Now, what is important, you see, Madhava derived the following series for approximation of pi. Derived as a proof. Madhava proved this. He not only proved this, he used this. This is a very, very slowly convergent series, converges to pi by 4 only very, very slowly. In spite of that, he obtained some correction terms and they used this series and obtained a value of pi as shown in the next table. Okay, next this, he obtained this value using that series. So that series is now, see, in Western countries, in the European countries, it is referred to as the Gregory series, and it was originally discovered by Leibniz in 1646-1716, and also by James Gregory in 1638-1675. And so remember, when was Madhava living? He was in 1350 to 1425, that period, at least 200 years before these people were talking about these series. And Leibniz were talking about that. Madhava discovered that series. He not only discovered it, he used it, and with the additional correction terms to compute a value of pi, correct to how many decimal places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. See, it is not an accident that you obtained this value. There was a lot of mathematics. Yes, given detailed proof of that, and that proof is given in Yukti Bhasha. And if you are interested, that is also available in the net. There are several sources where you can get the details of these proofs. The proof is basically a geometric proof. Now, see, Madhava series for sine. I'll just talk about that also, and that is the mathematics that I am going to talk here. So this is the English translation of the statement giving the power series expansion of sin x. Power series expansion of sin x. It is said in Madhava's own words, because so said Madhava. It was in one of the later verses, it has been mentioned like this. So said Madhava. That means it was exactly this way. Madhava said exactly this way. But that is the reason why I am saying it is in Madhava's own words. Okay, some to decipher what is written here, that requires some patience, some understanding of the way in which they were calculating, what they were trying to find. All those ideas are required. So I'm not going to all the details of that. Anyhow, in the next slide, I will see what it means. Basically, what it means is this. If R denotes the radius of the circle and S is the arc length, then Jiva, you know, the Jiva is the sign, vertical, altitude. can be expressed like this. This is what the previous slide means. In modern mathematical notations, this is what the previous slide means. Now, it can be easily verified that this is nothing but the series expansion for sin x. If theta be the angle subtended by the arc S of circle of radius r, then S is equal to r by theta. So gy is r sin theta. So substituting these in the previous equation and simplifying, we will get the well-known series expansion for sin x. So Madhava had discovered precisely this series and has given a proof, and the proof is now, even now, considered as valid with the current standards of rigor. Many well-known mathematicians have written about that, and they
What happened? Has he lost connection? No, he's still there.
Probably some connection problem might be.
But still, he seems to be logged in.
Might be some, usually on his phone when some call comes, it gets cut usually.
Oh, yeah, could be that, yeah.
Could be that.
So meanwhile, if there are any questions, you can put them on in the chat box such that, okay, then we need not lose much time. If someone has any question, please put it on the chat box such that when he comes back, we'll be able to, he has left the meeting, he'll be able to address them. Somebody clarify about the feedback form. People are asking about it.
Yes, dear participants, the feedback form will be displayed in the chat box after the next session. After the next invited talk, the feedback form will be given in the chat window. Thank you.
So if there are any questions, we'll keep them collecting such that Professor will be able to answer them once he comes back. Any more questions? Any questions? I hope you have got to know about the history of mathematics, mostly in Kerala. Of course, the history of mathematics in India was also dwelt upon. If anyone has a question, we'll be happy to collect them and give them to Professor, who will be able to answer them when he comes back.
Probably we can wait for a few more minutes. Where we'll be seeing whether he'll be joining back, and then if not, we'll continue with the next invited talk.
Yeah. Okay.
Okay.
He's supposed to chair the next session, so that's also we want.
Yeah.
Otherwise, we'll have to continue in this mode. Yeah.
Yeah. Ma'am, you can talk something
Okay. So
by
what,
then.
other than the fact that it's no, in fact, seeing people outside of Kerala as also outside of India in this venue is a very happy situation for us, because it is telling us that the mathematics that we talk here happens to matter to the external world. Okay, so that's the reason why we are happy to have you here. I hope you will get something or the other from here. The next talk, I believe, is on structures and symmetry. Okay, in fact, our professor was talking about the infinite series expansion of sine theta. It has some practical applications. So some of the engineers who are here, who are listening to you, will find something or the other to use when you people talk, either here or even in the other venue, where are the contributed talks happening simultaneously? No.
No, ma'am.
Okay, so yeah, so perhaps you can go back to the contributed talks also later on. Definitely, any experience is enriching. So we are hoping that you are not waiting just for the feedback form. You are waiting for whatever is coming through in these sessions here. I see somebody from Orissa here. The name is read as Ramachandra Pathi. Are you still there? Where are you from, Dr. Rosary? No. You're making small talk till the time that.
Good afternoon, ma'am.
Yeah, okay. So have you anything to say about Orissa mathematics? Mathematics in Orissa?
Regarding in maths in Odisha,
Yeah.
actually my subject is summative methods. I'm doing research.
Okay, so you're a scholar. Good. Okay, we'll wish you very well.
I'm working in a private college.
Okay, you're teaching also. Yeah.
Regarding Madhava also, I have done this little bit research.
Yeah.
Kerala mathematics helps me a lot.
Oh, that's good. So it's good that you are attending the session. Okay, you can keep in touch. I think our professor will be happy to help you in any matter whatsoever. Okay. So good of you to join us. Okay, glad to have you here. I noticed some other foreign names also. I don't know if I'm pronouncing it appropriately. I see one Ibocchouba. Ibochouba. Is that okay?
Yes, ma'am. Sorry.
Yeah, I see another name, Ibochouba here. So I was wondering if he's from Africa.
Oh. Sorry, ma'am. I also can't pronounce it that.
Yeah. And then there's Vivekananda Jaina. No doubt he is not a Malayali. So as I keep repeating, it's nice to have you people here. Okay, we feel enriched. We hope that you get something back.
Yes, ma'am. Yes.
Okay, is the time up? Organizers, do we go for the next session? Perhaps we'll have.
Ma'am.
Yeah.
Maybe somebody can call Krishnachandran sir up on the phone and see if he's okay.
Yeah, they're trying him on phone.
Oh, so he's probably on a call, is he?
I think the connection is not going.
Okay, all right. We can maybe wait a little bit for more minutes. I want to hear the end of his talk.
Yeah. Okay.
We'll ask him to conclude later on also. If required.
Yeah. The more time we wait, I think your mother has to talk more.
Okay. Yes. Maybe we'll give mother a break. It's okay, mommy. You don't have to talk.
Yeah, in fact, I have nothing to say.
And you're trying to get the audience to talk, but they're all sitting there with their muted. Yeah. It's like when I'm in class and I ask questions and the students try to hide behind other students.
For me, the problem is I'm talking to mathematicians. To talk to engineers is a little simpler. I won't be as as much questions as I am by mathematicians.
Hmm.
Dr. Rosary, where are you from? Dr. Rosary, where are you from?
She says she's from Chennai.
Chennai, okay. Yeah. Oh, she has typed in the message, yeah.
Mm.
Actually, we would have hosted you here and we would I have asked you, how is the food here? Are you comfortable, etc. So now nothing like that.
Mm.
In our international conference, we normally talk to people. We ask them whether they are comfortable in our own environment, whether they need something else. Now those questions become redundant. But still, let's hope that all of you are safe and you're keeping yourself safe, because as far as we know, Chennai is not all that clear. So similarly, okay, Dr. Santosh Singh, where are you from? Dr. Santosh Singh, where are you from? Mumbai. Okay, so Maharashtra is the most affected, and perhaps Mumbai is also the most affected area. I hope you people are safe, your people are safe, and everything's fine. Okay, nice to have you here. Okay, these are not the days to travel.
So do you have an emergency chair or a backup chair or somebody, or should we wait for a little bit longer for the chair?
If KBM sir was here, we could have asked him to chair the session. Has he logged in? KBM sir said that he'll try to log in. He has a bigger problem of internet.
Oh, GB ma'am, maybe?
GB or Sijus, one of you?
I saw
Okay.
I saw
Okay.
Sushant sir around as well.
Everyone are stranded. All of them have a network issue. GB ma'am is also not able to join.
Okay.
Krishnachandran sir also is not able to join. So I think we can continue.
Yeah, KBM sir is here. KBM sir.
Yeah,
Sir,
KBM sir.
can you chair? Sir, can you chair this session? Sir, KBM sir, can you hear me? Can you chair this session? Sonia is speaking.
Krishnachandran sir is coming, I think.
Okay,
Okay.
then,
Well,
yeah.
in that case.
Fine, yeah.
Yes,
KBM
yes.
sir has a big issue.
I just saw Krishnachandran sir. I just saw.
When
It
did I
will take
miss
a
you?
minute
Yeah,
or
yeah.
two after.
Yeah, so he's back.
Okay. she wanted her chair. She also wanted the last part of the session. My daughter.
Yes, sir. If you want to finish your talk, and then we can continue.
She wanted both. What do we have?
So, there was a net issue here.
Yeah.
So it was getting
yes.
frequently broken. So the problem is I did not know whether you are hearing on me or not. That happened when I used to take classes also.
We couldn't hear you at all. Yeah, we couldn't hear you. Neither could we see you. We couldn't hear you. We couldn't hear a word. We couldn't hear a word when we lost you.
Yeah, I think he lost connection. Yeah.
Yeah. Now, can you hear us now? Can you hear us?
At what?
Yeah, we lost.
Yes, at what time?
We lost you while you were talking about. Okay, I think the sin theta was completed. Yeah,
The last
series was completed.
Okay.
And you
No.
wanted to say something more. Yeah, so we are waiting for that something more. Yeah.
Oh. So what shall we do?
Maybe finish your
share.
talk, sir.
Eh?
You can even speak. If you can't present, you can even speak. We'll listen to you.
Okay.
Yeah.
So Sonia wants you to complete the talk. Sonia wants you to complete the talk.
Okay, then let me go to the present.
Okay, sir. Okay, sir.
If you can present, well and good.
Probably he has left the meeting.
He will be back, I'm sure.
Okay. What about the situation in Ireland, Sonia?
It's fine. I think most people who are working in offices and can work from home are working from home. Schools just went back, so we will have to wait and see what the effect of that is. Next semester, I think all universities, most universities anyway, are going to have their classes online. And yeah, but there's actually it's the situation is quite bad in say people working in factories, and especially from immigrant backgrounds and poorly paid workers. They're living in very close accommodation together, just like everywhere. There's definitely like a class divide in how people are managing through the pandemic. So we are okay. My husband and I are working from home, and well, I'm not working, he's working, and so we are more or less safe, and older people have been advised to cocoon themselves, which is to stay at home and if possible get all their shopping delivered, and like not leave if possible at all. So it's kind of okay. The medical system is holding up, I think, which is probably the most important part.
Yeah, the medical system is the most important, but probably here also the same situation. Medical system is holding up everything. If not, it would have gone up, shooted up.
Okay.
But probably
I'm glad I'm
for
not
quite past few days it is shooting up.
Yeah, it's the same everywhere. Yeah, it's the weather and everything.
Right. So he's back again. So let's listen to him.
He's back.
Yes. Okay.
Still, I think I'm afraid still I am having problems. The presentation
Okay,
is
sir,
not
you can just without presenting, you can just conclude it without presenting the slide. Okay.
Oh no, it's fine. Yeah.
It's okay.
Okay, can you now see?
Yeah,
Yes, sir.
Right. Yeah.
Can you hear?
Yeah.
Yes, sir.
Okay. So, was this the last slide you saw?
Yes, exactly.
Yes,
yeah.
Okay. Then I'll continue from here.
Yeah.
Okay. Now, see, what I wanted to say was, this is the way in which Madhava formulated the series. Not exactly these notations as is given in the previous slide. It is so many words. So we have to decipher this statement. When you decipher this statement, this is what we get. Now, if we use modern notations, theta is the angle subtended by the arc. Then we have the jiva, the vertical altitude is r sine theta. And substitute and simplifying, we are getting this exactly the series expansion for. Suitable computation in this form, it can easily calculate the values of sin theta, and that reformation is given in the next slide. Okay, that requires much explanation, the meaning of all those things, but this was the form in which Madhava used to compute the sine function. This is the form about which I wanted to tell more. He also had a similar expansion for the cosine function. That's also given in the next table. And next slide. Madhava did not stop with finding these expansions. He actually applied that to construct a table for sines. And the table is given in the next slide, first half. The first column is given degrees. 3.75 degrees, multiples of 3.75 degrees. The values are given using the Kabayani notation in terms of as if they are some lines of some verses. No meaning, not meaning, only looks meaningful sounding sentences. So when you transform them to modern notations and calculate, we get the values of sin theta as given in the last but one column. Last but one column are the values corresponding to the values obtained by Madhava in modern notations. In the last column we have the modern values. You can see how much difference is there. How much difference. Value of sin derived from Madhava's table, last but one column. In the last column we have the modern value of sin. The difference is only in the last digits. This is correct up to 1, 2, 3, 4, 5, 6, 7 or 8 decimal places. Okay. The remaining values are given in the next slides. Values up to 90 have been calculated. And these values are given in the form of a verse so that can be easily remembered. Now, see, what I wanted to say is what is contemporaneous about these achievements. You see, in the discussion on history of mathematics, usually the historians emphasize the mathematical aspect of these discoveries, but I wanted to focus on the computational aspect. This aspect is not generally emphasized. I have not seen that emphasized in any of the writings that I have come across. Made extensive Googling, but still I could not find any references to this aspect. So what I am going to say is perhaps something new, not being discussed in the available literature, to my knowledge. And I cannot say not at all, because I haven't come across this. The first point that I wanted to say is the way in which the results are formulated, the formulation of the results. The results are formulated in a step-by-step procedure. Write something. Next line, write something. Do this calculation. Do this, like that. So they look exactly like algorithms. This may be a little too far-fetched to say that Madhava had a sense of algorithms, but I think we have to say he anticipated a step-by-step procedure. Even the terminology used refers to algorithm. For example, in the next slide at the last line, yesterday was Yukti Bhasha has used the term Kriya Kramam, the order of the operations, which can be translated into a procedure or an algorithm. So we can give these, the method of computation as examples of ancient algorithms, not ancient algorithms that were used by mathematicians in Kerala. Then the second thing is Madhava has used polynomial approximation. That looks so trivial, but it's not that trivial, because see, in computer languages, in C, Java, and other languages, see, we use sin x, cos x, and all those functions are used. They are all built-in functions. But if you ask a computer science student or a professor how sin x is calculated in the language, I am afraid they will not give an answer. They will not give an answer because see, that is not generally discussed. That is hidden inside the built-in functions. So the procedure used is in not all. There are special hardwares, but in some of the so in some cases, there are several cases where the sin and cos are calculated using polynomial approximations. So Madhava again was anticipating a polynomial approximation for the computation of sin x. That is what one of the important aspects of that result. A third point is, see, you can see some numbers there. What Madhava has done is to pre-calculate the coefficients. Pre-calculate the coefficients and then applied the polynomial approximation. Almost the same thing is done in many of the compilers. See, many compilers are not using the Taylor series approximation. They are not using Taylor series approximation because a truncated Taylor series is not the best polynomial approximation. Truncated. If you take a polynomial degree 10 and use the Taylor series truncated at degree 10, that is not the best polynomial approximation. There is a Remes polynomials are there. So in modern compilers, the coefficients are not the coefficients obtained from Taylor series expansion, but those coefficients are pre-computed and the values are calculated. So here also Madhava is using the same idea, pre-computing the coefficients to help him simplify the computations and get the table. And this is also an interesting observation. I've not seen this anywhere else. See, he uses, if you look at the way in which the series is calculated, it's not apparent from the way in which is shown in the slide. Madhava is using what is known as the Horner scheme for the computation of polynomials. Okay, the Horner scheme was discovered by this William George Horner. It is in the 18th century, 19th century, 1786 to 1837. So it must be discovered in the 19th century. But Madhava was using that consciously. Okay, this is only a simple method for simplifying the polynomial calculation to reduce the number of multiplications. The idea is to reduce the number of operations. So for example, here we have a polynomial like this. So generally, see, if we look at it, how do we calculate this? We have to find a0, we have to find the x square, x cubed, x raised to n, and then multiply x by a1, x square by a2, x cubed by a3, like this, and see how many multiplications we are making. The question is, can we have a scheme where the number of multiplications can be reduced so that calculations can be simplified? And Horner scheme is a method for doing that. It is shown in the next slide. Okay, I think it is very clear. A0 plus x into, entire expression is in brackets, a1 plus x into, like that, and apply the scheme as shown below. It's very elementary, very elementary. Exactly this scheme is used in Madhava's reformulation. Precisely this has been used in Madhava's and the reformulation of the method. That is the one of the interesting observations that you have to make, and that is one of the contemporaneousness of Madhava's numerical computation. Okay, so these are all the things that I wanted to say about that. Okay, there is one more point is there. In computations, see, wherever you have to find sine, we will also require cosine. Generally, sine and cos go together. So the methods for computation of sine and cosine are usually combined together. So the procedure will produce both sine and cosine. That is how the routines are written in the formulations given in the works of Madhava and his disciples. Again, the same scheme is followed. Both sine and cosine are calculated simultaneously. Okay, that's all. Now, that's all that we wanted to say about the contemporaneous. So if you are interested in knowing more about this, see, as our dear Dr. Sonia Balagopalan was talking, I was interested in contributing articles to Wikipedia. And I found a lot of gaps regarding the Kerala mathematics. So I contributed several articles related to Kerala mathematics. These are some of the articles that I have contributed. It's an article on Madhava series, article on Madhava's sine table, and an article on Tantra Sangraha. There is also an article on Aryabhata's sine table. Aryabhata has also a sine table, and he has a different method of representing numbers by letters. Aryabhata's scheme is different. It is called the his method is different. And The significance of Aryabhata sign table is that it is the first sign table ever constructed in the history of mathematics. That is the significance of Aryabhata sign table. You just can refer to these articles in the Wikipedia and get much more information. Most of the material in these articles are written by me. Since Wikipedia is an open encyclopedia which anybody can edit and contribute, many others might have contributed in refining what I have written. So I cannot possibly claim that everything that you find there is mine, but most of what you see there. I started the articles and nearly completed the article. Only some fine tunings may be there here and there. That's all. So I would suggest that you read this. So it is so easily accessible. If now you have got your laptop, you can just start Wikipedia and search for these articles. And there are several references are also given, and that will give you a better insight into these ideas. But I think the references have no discussion on these contemporaneousness of the numerical computations. Okay, that is all. And so let us pay pranams to the genius of Kerala mathematics. Let us express our gratitude to all our great forefathers. And thank you for giving me a second chance to explain what I could not do because of internet problems. So thank you for your patience. Thank you. Thank you so much. Thank you.
Thank you, sir. I think, in fact, we also should give you pranams because we were also taken back to history and we found in fact, the content that you delivered was really interesting. And I believe we can take one question at least right now, if there are any. In fact, I asked for questions earlier, but they were not forthcoming. Let's hope that there's one question. Thereafter, we'll go to the next session. Anyone has a question?
Okay.
Has a question?
Okay. Anyway.
If anyone has a question, please unmute yourself and ask. Okay, so I suppose we'll share your email ID with the people such that they can, in fact, some people expressed interest in knowing things a little further. Perhaps they'll ask you to talk in their own colleges or something like that. So if you don't mind, we'll wait for such interactions at a later stage. So we'll go.
I'm only happy. I'm only happy. As I told you, I never hesitate to talk on these.
That's what I conveyed to them. You will always be happy to help whosoever wants any understanding of further details in any area of mathematics, for that matter. Okay, thank you, sir. Let's hope that let's hope that the organizers take on from now. Thank you.
Thank you. Thank you. Yeah.
Thank you. Thank you, Professor Dr. V N Krishnachandran, for having delivered a very informative talk. We also thank Dr. Sonia Balagopalan for having chaired the session. Thanks to all participants. Without taking much time, we shall move on to the third session of invited talks. We have with us Dr. Sonia Balagopalan, Dublin University, Ireland, for delivering the session on structures and symmetry. The chair for the session is Dr. V N Krishnachandran, Conference Chairman, ICDAM 2020. We request Dr. V N Krishnachandran to introduce the distinguished speaker.
Okay, thank you. Thank you. So now I am changing roles. Thank you for giving an opportunity to introduce Dr. Sonia Balagopalan. I'm only happy to do that. I'm really happy. Because she's a very different kind of personality. But I think I must explain that. I sometimes I see a part of myself in her. Sometimes. See, she graduated she took a B Math course. If I remember correctly, when everybody else in her neighborhood, everybody else of her age were craving for a course in professional course, maybe engineering or medicine or things like that. She did not go for that. She went for studying mathematics. That is the type. You see, so when I say I see a part of me in her. When I was a student half a century ago, at that time there was no engineering, but every bright student was going for either physics or chemistry, and nobody was taking up mathematics. If a student is not able to get any course, any science course, then only they used to join for mathematics. But I took up mathematics, and the principal, St. Thomas College, my father, Thomas Muthan, asked me, was it an error that you took mathematics? I said, no, I chose mathematics because I like that. Okay, so Sonia was a person who chose mathematics because of her passion for mathematics. She took her degree from the Bangalore campus of Indian Statistical Institute and then went on for higher studies to Ireland. She took a MSc and PhD from the National University of Ireland in Maynooth. After that, she spent about 1 year as a postdoctoral fellow in the Hebrew University in Jerusalem, and then again went back to Ireland, and now is teaching at City University of Dublin in Ireland. A young scholar having great future, a great career in mathematics. Definitely. That she will, I'm sure, contribute much to mathematics. Her area of interest is, as I understand, something like an area which is an intersection of algebra, combinatorics, and geometry. In the higher levels of mathematics, it is very difficult to say the area because what we talk about in other areas are interdisciplinary. Something like that is happening in mathematics also. The disciplines are the classical divisions of mathematics. Algebra, geometry, calculus. See, there is not much difference. At the higher level, all these come together and they interplay. Will have applications like that. So she is now working in some area connected with the, so it's an intersection of all geometry, algebra, and combinatorics. I'm happy to introduce her with much love and also with much respect also. I invite Dr. Sonia Balagopalan to present her talk during this international conference. Please, Dr. Sonia.
Thank you very much. That is a very, very flattering introduction. I'm sure I don't deserve any of it, but I will. Okay, so how much time do I have? I think I will start at 12 on the dot. And can everybody stay for 45 minutes, maybe? Hopefully, part of it at least. Okay, right. So I will start presenting. I can present here, and if I click on present, let's have a look at what the screen looks like. I'm presenting my screen. I'm just testing out my screen. I'm presenting. Okay, right. So maybe I just need to go back to that slide. Okay, can everybody see a title slide?
Yes, yes.
Okay, thank you very much. Okay, so I thought I'd talk about structure and symmetry, which is a topic I very cleverly took because I don't want. Anyway, first of all, thank you very much for your invitation. It's always nice to revisit Thrissur virtually, at least, and I can see my parents' living room on my mom's screen, so that's always nice. And I in turn welcome you all to Ireland and my kitchen. So. But thanks very much, and let's talk about structure and symmetry, which is a topic I chose because I had no idea what I was going to talk about, so I thought I'd leave something very generic. Okay, so the area of mathematics I work in generally, it's called combinatorics. But what is combinatorics? Well, I mean, there is combinatorics, the human activity, which we do pretty much every day. If you're a child, you play around with blocks which have different shapes and which have different colors and things like that, and then there's something in our brains that make us kind of go towards patterns and recognize patterns. That's just part of being human. That's combinatorial activity. You're going on a holiday somewhere, well, not right now, but in normal times, you go on a holiday somewhere and then you ask, oh, do I have enough shirts? Do I have enough trousers? Do I have enough skirts? And so you're kind of thinking about combining things together and putting them together, and this is a certain element of counting. You go to the shops, you hand over some change, and you want to know how you can make, say, 2.5 rupees out of various different kinds of coins. These are all combinatorial activities. We may recognize it as mathematical activity, but we are not sure if it's part of academic mathematics or not. I mean, to a great extent, I still am not. But what is combinatorics? When does combinatorics appear in mathematical form in the history of this human activity that we call mathematics? So usually, pretty much every branch of mathematics evolves from the attempt to solve some problem. So somebody asks themselves or somebody else a question, and people are trying to solve it. Some problems are interesting, some are not. And we have and you have questions. So initially, a lot of what we recognize these days as combinatorics came from India. Another source of mathematics historically has been Greek civilizations, but they didn't really care too much about counting. Like when they look at a triangle, they saw the properties of triangles, whether it's like a right triangle, whether it's an equilateral triangle, and what are the lengths and what are the relationships between various measurements. But if you're a combinatorialist, you kind of think of a triangle as a representation between objects and their and relations between them. But there's also another huge part of combinatorics, initially at least, was counting. So, and you see a lot of these counting problems in old texts, from including the Rind papyrus, I think it's called, the very old Alexandrian fragment, but also in ancient Indian texts. So a lot of early combinatorics came from texts like the Bhagavati Sutra, which is a Jain textbook, and also, but I couldn't find a primary source for it, so I picked a problem from the Sushruta Samhita. So what that is it's an old text of medicine, and it's an Ayurvedic medicine and surgery text, and it still survives to modern times, a lot of it, and it has been translated into English. So here on the right, you see an English translation of the Sushruta Samhita, where this chapter is basically one long calculation. So he wants to know how many combinations of tastes you can make. So there are these tastes: Madhura, which is sweetness; Lavana, which is saltiness; Amla, which is an acidic, sour taste; Tikta is bitterness, Kaduka is pungency, and Kashaya is like an astringent taste. So if you speak any Sanskrit or you speak Indian languages, you probably know these words in some form or another. And he basically went and did the entire calculation by listing every single combination of tastes you can take, and he counted the answer as 63. As modern mathematicians, you would go, okay, there are 2 to the 6 possible combinations. Well, take away the one empty combination and you have 63. And funnily enough, this is an old combinatorial list trick. He put that computation into chapter 63. So this is something combinatorial. This is like our sense of humor right here. Okay, right. So also, if I'm speaking too fast, or if you have any questions or something, do drop a question in the chat box and I'll try and get to you when I can. Okay, right. Okay, so far, right. So that's combinatorics. And what about, okay, so that's combinatorial stuff that appears in, and like a lot of Asian cultures did have a lot of combinatorial activity going on. They were parts of literature, or people were trying to do philosophy using this. And then it kind of arrived in Europe through various methods. So one of the great mathematicians of yore, Leibniz, who is also credited with the invention of calculus, when he started studying mathematics, for him, he came through philosophy. So he wanted to mathematically prove the universality of human existence, and he wanted to prove the existence of God with logic. So, I mean, these are probably activities that we no longer recognize as mathematics, but when he was talking about but he wrote a book called Dissertatio de Arte Combinatoria, and this is the first time in Latin or English that this is the origin of the word combinatorics. This is the first time this word combinatoria or combinatorial appears in the literature that we know of. Okay, so and he starts so he's doing some physics, metaphysics stuff I don't understand, but it does involve combinatorics in the sense of counting, and he has counting problems in it, and he talks about little identities involving binomial coefficients. Maybe they use different words, but that's what is going on. Okay, and then also, but he did get a lot of his ideas from the East. So he was in contact with Jesuit missionaries, and they sent him a copy of the I Ching, which is an ancient Chinese text, which is a book of divination. So again, this is, these days, in those days, everything was kind of, a lot of the stuff they did those days we don't recognize as science anymore, but that was their intellectual activity of the day. So he looked at this and he kind of realized, so if you can see this very faded picture, this is Leibniz's copy. And what he was doing was he's actually numbered these things. So here's a 1, a 2, a 3, and so on, because he basically looked at it and he goes, wait, these are numbers. These are the numbers from 1 up to 64. And so basically, if you have all broken lines, that's a 0. If you have an unbroken line, that's a 1. And every number from 1 to 64 can be written as a combination of zeros and ones and he basically just recognizes what we now call binary arithmetic, which is the foundation of all sorts of mathematics that makes the digital world possible. So we can thank the Chinese people who wrote this and Leibniz who recognized it for that. Okay, so and then to make it even more mathematical, so time passes and people are getting rich, and there are a lot of rich people with a lot of leisure, and they start amusing themselves with activities like gambling and questions about predicting the future and throwing dice and stuff like that. And this was probably the biggest driver of the development of combinatorics in the West. So Jacob Bernoulli writes a book called Ars Conjectandi, which is probably the first textbook on combinatorics and probability. And he does a lot of what we recognize now as combinatorial methods of counting various objects under various restrictions. And he thinks that that to learn to count things properly is a most eminently useful and worthy activity, which I completely agree with. Okay. So that was Bernoulli. He was he was working in probability, but at the same, and so that was mostly counting. But at the same time, there's another part of very integral to the activity of combinatorics, which is that of very discrete patterns. So here is one of my favorite works of art, and the expression on that, the a creator's face is so relatable to me. This is exactly what I look like when I think about mathematics. And if you look very carefully at that picture, what you see is in the top corner there is well done if you recognize that for yourself. That is a magic square. Okay, so a magic square, if you haven't seen one before, this is a very cool magic square where every row, every column, and the two main diagonals, and also the top, the 4 2x2 squares at all the corners, and the middle 2x2 square, they all add up to the number 34. Okay, so this is a very, very cool magic square. And also he's using a little trick here where he does this engraving in the year 1514, and the 1514 is at the base of this magic square as well. So artists are looking at mathematical patterns, and magic squares are very old. The first known magic square appears in China, and they use so because there are these additive conditions that magic squares have to satisfy, they went off in the direction of thinking about simultaneous linear equations and things like that, which we all study a lot in school. Okay, now, so okay, so then we move on to Leonhard Euler. So I know this is like a lot of about the history of mathematics, but the thing I realized was, a lot about the history of many branches of mathematics, but the history of combinatorics is something that I had to seek out and try and find out some stuff about. Anyway, so Leonhard Euler, foremost mathematician of his time, maybe one of the top mathematicians of all time. So if anybody had to name the greatest mathematicians ever, Euler would definitely be one of them. So if Euler works on something and he tries to solve a problem and he can't quite solve it, that's immediately motivating to the entire world mathematical community, where they're like, oh, if Euler couldn't solve it, I should probably give this a try. Or, so he basically kickstarts branches of mathematics just by thinking about it and writing a note or two about it. So some of the things he's done is he worked on the 7 bridges of the Königsberg problem, which is a puzzle that people of the city were asking each other about, whether you could go through all the different islands of this city by passing all these bridges. And he proved that you couldn't by basically turning a real life situation into a graph, which is a set of objects together with their relations that, and so you connect to, so he noted various parts of the city by nodes, and then he connected them with a little line, with an edge, if you could go from one to another. So that was basically, everybody says, okay, that's basically the beginning of graph theory. So people started studying these objects called graphs in their own rights and so on. Another thing he studied was geometry, and he wrote a paper called The Doctrine on Solids. And in there he has a proposition. So if you look at the last formula there, he's like, okay, if this is the number of corners, this is the number of edges, this is the number of faces, and if you put them together and they satisfy this formula. So all 3-dimensional solids have that. But the Platonic solids were known to everybody, and even before then. But also, if you have, but he proved this more generally for other solid. He didn't prove it. He actually stated that there was a problem with this proof, but it was proved recently. Is everybody okay? Okay, right. So moving on, another thing he did was he actually wrote a lot about, he said a paper on magic squares. They weren't about magic squares, but he considered the problem of the 36 officers. So what you have in with the 36 officers, it was something somebody asked him, and so you have 36 officers. They come from 6 regiments, and in each regiment there's an officer of 6 different ranks, and he wants to know whether you can put them together in a way that nobody so you want to make them march in rows and columns, so that in no row are there 2 officers from the same regiment, and in no row are there 2 officers of the same rank. So, and that's a situation that we now call, that kind of arrangement is something we now call a Latin square. And Latin squares were also known way before Euler. I mean, Indian mathematicians knew them, and they used to know to work that. They used Latin squares in order to create big magic squares and stuff like that. Anyway, so Euler looks at it, and then there were if you change that question a little bit to whether you could do the same thing, whether you could do the same thing. No, sorry. He said, okay. So he conjectures that this is not possible for 6 by 6, and and then he also conjectures that you can't do this for any n by n, where n is some oddly even number, which is a number that's divisible by 2 but not divisible by 4. Okay, so in 1901, somebody actually wrote down all the possibilities, and by exhaustion proved that you can't actually do this. But also, but then later in 1959, 2 Indian mathematicians and an American mathematician, so that's Parker, Bose, and Srikhande, proved that it's actually, well, Euler was wrong. They're called Euler spoilers, that you do have magic squares. Sorry, mutually orthogonal Latin squares in different dimensions, for different orders, different values of n, other than 6. Okay, so that's. So okay, that was a problem that lay open for 250 years. I mean, and they finally solved it. Okay, so this is all combinatorial stuff. We would look at it and go, oh, that's a combinatorial problem. It's not exactly a counting problem. It's more of an existence problem of certain configurations. So that's, again, but we still don't have a branch of mathematics called combinatorics. It's not being taught. It's basically being used as a set of techniques for various other things, or as amusement. Okay. Okay, so I want to step forward another 80 years or so, and here is a copy of the Ladies and Gentlemen's Diary. So, and it says it's designed principally for the amusement and instruction of students in mathematics, containing many useful and entertaining particulars. So this is like a little science magazine for students. So they come out once a year, and there are lots of problems. There's lots of like little write-ups that you can use, and people who are mostly homeschooling their children or tutors would look at this and kind of find things to do. This is the days before state-sponsored education and standard textbooks. So there was like a big kind of private sector of educational materials that people would choose and teach from. Okay, so in the Ladies and Gentlemen's Diary, if you look at the bottom right corner at the very end, there is a query number 6 by the Reverend Thomas Kirkman. So I've transcribed it over here. So he's the Reverend Thomas Kirkman from Croft near Warrington, and he wants to know, 15 young ladies in a school walk out 3 abreast for 7 days in succession, right? So you got 15 girls, and they're walking in 7 little rows, and there's 3 of them in every row, and you want to there are 5 rows in every little row. There are 3 people, and they go for walks every day, and they want to be arranged so that no 2 shall walk twice abreast. And this is called Kirkman's schoolgirl problem, and it became immensely popular. So every time in mathematics now, if you say Kirkman, people go, oh, the schoolgirl problem. And Kirkman absolutely at a stage came to hate that. He was like, I'm not just the guy who thinks about schoolgirls, I'm interested in other parts of mathematics too. And he was. So Kirkman was born in the English city of Bolton. He was the son of a cotton merchant, and when he finished school at 14, his tutor said, oh, you'll definitely get into Cambridge, you're great. And his dad said, no, we have a family business, why would you go to college and waste your time? So come and work in the family business. Okay, so he worked in the family business for 9 years, and he was sick of it, and he defied his father, and he went to Ireland, unlike me, whose parents encouraged and paid for me to go to Ireland. But Kirkman had to run away from home and study in Trinity College Dublin, and then he came back and he became a rector in a church in Croft with Southworth. Okay, and then he married a woman, and he worked as a tutor for a little while, but also after a while his wife inherited some property, so he didn't need to work. Being a rector was basically like being a newspaper columnist or something. He had to give like one sermon, and it didn't take any of his time. So he kind of went back to his love for mathematics, and he did a lot of mathematics. He discovered Hamiltonian graphs before Hamilton, and he knew Hamilton because Hamilton was based in Ireland, and he knew him from his days in Trinity. He discovered what we call Steiner triple systems before Steiner did. He worked a lot on group theory. He worked on hypercomplex numbers. He worked on polyhedral combinatorics. Right till his death, he was doing mathematics, and he published his paper on knot theory at 78. He was a very prolific mathematician, and he well deserves to be known for a lot more things other than a problem about schoolgirls. But he felt very isolated. He was living in a little village, and he wasn't near anybody. And also he had some kind of fights with people, with Cayley and Sylvester. So Sylvester claimed credit for something Kirkman did, his solution to the Kirkman problem. And Kirkman said, well, I haven't even been to Cambridge, so what are you talking about? So they all had these little arguments about who deserves credit for that. And, but they're all dead, and we have the beautiful mathematics they invented, so maybe we shouldn't worry about that too much. So Sylvester and Cayley were also the same. They both went to Cambridge, but Sylvester never got a degree from Cambridge, because back in those days you had to be a member of the Church of England, and Sylvester was Jewish. So basically he was awarded a degree by Trinity College Dublin, because they didn't care if you were Jewish or not. So he got his degree there, but he couldn't really find a position. He went to America, he came back, and he decided to change careers, become a lawyer. And Cayley as well, he went to college, and he decided to be a lawyer. They both had difficulty finding academic positions in mathematics, which is very relatable right now. Okay, so they were working as lawyers, they met each other, and they started a 40-year collaboration where they talked to each other a lot, and they inspired each other to work on various parts of modern algebra. So they were also very great mathematicians, but they didn't quite get on with Sylvester, who thought that they were parts of the establishment and they were trying to keep him out. But it's a sad story. I would have thought they would have got on really if they were near each other, but sure. Anyway. Okay, so these are various combinatorial things that were being done around the world, and then more and more people started getting more education, and people started thinking about things, and also various questions started coming up, not just mathematically, but also people were thinking about graph theory. There was the four-color map conjecture, which drove a lot of development of graph theory. People started understanding chemistry in more detail at the molecular level, so they were looking at the structures of chemical compounds. People were thinking about partitions, so more kind of complicated counting problems. The people were attacking them with things like generating functions, which came up because we knew enough analysis to work on things like generating functions, and then people were doing statistics and communications and things like that. So various things like design theory, information theory, and all those came about as well. Okay, so that's, how am I doing for time? I'm 20 minutes in, so another 25 minutes. Maybe I'll finish early. We'll see. Am I talking too fast? No,
it's fine, Sonia, it's fine.
Okay, thank you. All right, okay, so that's early modern combinatorics, and if you want to know more about the history of combinatorics, you can, hold on. Yeah, okay, there's this lovely book by Wilson and Watkins. It's called Combinatorics, Ancient and Modern, and they have a lot of essays collected about various parts of mathematics, so ancient combinatorics and how it developed in various parts of Asia, and about modern combinatorics, how it developed. So it's a good book. All right. At this stage, we're talking about the early 20th century, and combinatorics is pretty much a branch of mathematics now. People have inherently, so it shows up in mathematical problems. People have sort of hopefully accepted the mathematical nature of the combinatorial activity that we do. And here is Dorothy Maud Wrinch, who was a mathematician and a chemist, saying, for some reason which is not at present clear, the theory of the combinations of different sets of similar possibilities, which can be conveniently represented as the distribution of balls in boxes, is of utmost importance in many branches of science. So she was a chemist, so she would know. And she was also an associate of Russell, and she worked on logic and various areas like that. And this she wrote in a review of a book about combinatorics. So a book by McMahon, who was a combinatorist, and he was a contemporary of Ramanujan back in the day in Cambridge. So now people are writing about combinatorics as a branch of mathematics. There are books which are called things like combinatorial analysis and things like that. So it's about time people should start teaching it in colleges and schools and stuff, right? Okay. So and people are writing books, but we still haven't decided what combinatorics is, and it's actually a very hard subject to define. So, I mean, basically, it's up to you what you think, what you recognize as combinatorial, and what you think combinatorics is. But here is Claude Burge, who is a very famous graph theorist, who thinks that combinatorics counts, enumerates. I don't know why he says that twice. I think counts is the same as enumerates, but French people, yeah? Okay, so combinatorics counts, enumerates, examines, and investigates the existence of configurations, which he earlier defines as a configuration arises every time objects are distributed according to certain predetermined constraints. Anyway, so configurations with certain properties. And with combinatorics, one looks at their intrinsic properties and studies transformations of one configuration into another, as well as subconfigurations of a given configuration. I like that definition, but it's up to you. I mean, we still haven't agreed on what a good definition of combinatorics is. But as something that studies the intrinsic properties of configurations, and intrinsic as opposed to, say, for example, again, you look at a triangle, we don't care whether the triangle is embedded on a sphere or a hyperbolic space or what it is. We just know that a triangle is three things joined, where everything is joined to everything else, right? So that's intrinsic to the triangle, and extrinsic is all about sort of ambient spaces and things like that, which we don't generally care about in combinatorics, right? Okay, so I think we probably define combinatorics. Let's talk about a little bit more specific mathematics. So Kirkman's problem, people have found different solutions to it. There are 7 different solutions, and I won't tell you what different is, but they're in some sense essentially different. Okay, I leave that to you. We want, if I wrote down some 7 sets of 3 by 5 matrices, it's not going to mean anything to you. But what about if we tried an easier problem, which is we make it a little bit smaller? So you can try Kirkman's problem, and if you write it down, you kind of find out that you will try a few things, and then suddenly you painted yourself into a corner. You'll have to backtrack and find more things. So it's actually a little bit harder. Okay, so maybe if you try something easier, if you have 9 young ladies in a school and they walk out 3 abreast for 4 days in successions, and it's required to arrange them daily so that no two shall walk twice abreast. Okay, right? If you can't solve a problem, try an easier one. So what about an even easier problem where you have 4 young ladies in a school and they walk out 2 by 2, and they do that for 3 days in succession, and we want to see if we can do that. Well, that's something that you could just get a piece of pen and paper and write, right? So you can just say, okay, first and second, third and fourth, first and third, second and fourth, first and fourth, second and third, done, right? Okay, that's cool. And if you are used to doing mathematics, you know that if you have something like this, it's also kind of useful to draw pictures. I'm sure there are loads of graph theorists in the audience, so this is something that you would do, right? So what you've done is you've taken the complete graph on 4 vertices and split that into parallel classes. Right, okay, that's modern language, but back in the day we weren't thinking about that. Okay, what about the slightly harder problem then? So in the harder problem, you could do the same thing. You could go for day 1, you put them in a row, and then basically you can turn the rows into columns, and in day 2 you could have that. So you could write that out like this. So you could put them in a column like this, and then what you want 2 more days. So you could go with the diagonal AEI, and then B has to go with F has to go with G because it can't be on this row, or anywhere else, and C has to go with D has to go with H. And is it possible to do a 4th day? Well, let's see. C, then you have to send A and F and H together, B, D, and I together, C, G, and E together. Don't worry about it too much if you didn't follow that, but I'll give you a second to look at that, right? Does this remind you of something? If I put those girls together, and if it on the next day it was another day, does this remind you of Euler-Sladen squares? Maybe. Okay, right? So, well, anyway, so here it's a nice and pleasing pattern anyway to look at, right? So, sorry, should go the slide forward. Okay, so if that is the case, then you can write down there how we are going to send them out on a walking trip on days 3 and 4 as well. Okay, so that's Mr. Kirkman. Okay, so and then I'll leave the big question to you. Of course, it's left as an exercise, right? Another thing that makes combinatorics quite respectable is sometimes when you have a hard mathematical problem, at the core of it there is some combinatorial configuration you just can't break. Okay, so Julius Plucker was working on plane cubic curves in 1830s, and so that's like an equation. So y is equal to some cubic equation of x, and then he's looking at the space of solutions in some some space, and then he is and then he also on the real plane, and then he looks at them and he realizes that a general plane cubic curve has 9 points of inflection. Don't worry about what that is, and they lie in 3s on 12 lines. Moreover, given any 2 points of the system, exactly one of the lines passes through them. All right, and this is a configuration that we now know, and it's called the affine plane of order 3. Right, so here is a little flashback to the Kirkman problem. So Plucker was thinking about this. Plucker knew Sylvester. He told Sylvester about this, and Sylvester knew about this as well. He probably told Woolhouse, who is the person who inspired Kirkman to think about the other problem. So, maybe it all goes back to Plucker, and maybe Kirkman wasn't as originally thinking of this up himself either, because there were previous questions in the Ladies and Gentlemen's Journal about these configurations and stuff like that. But anyway, here you have a picture, and according to me, I think that's a very pretty picture. So what we have here is points and lines. So when we talk about points and lines, we're not talking about straight lines. There's no concept of betweenness that we generally have in classical or Euclidean geometry, right? A line is just a set of points which are what we have instead of betweenness is incident. So they lie together. So it's just a set. If they're in the same set, they're incident, they're on a line. Okay, so here you have all these different parallel classes. So you got, I should have colored that, but I kind of was lazy and I didn't. But anyway, it's a nice picture. You can look at it and you can see how the various points and lines are parallel or intersecting, and there are 12 of them and so on. And that's exactly the same one that we saw previously with the 9 schoolgirls. Right, okay. More algebraic geometry, people are discovering irreducible configurations that they simply cannot get around. So this one is Kummer was studying a quartic surface, and it's a I don't understand geometry really. So, I mean, this is Greek to me. So he has projective three-dimensional space. Okay, I kind of think I know what that is, but what's a node? Anyway, so so he studies some very complicated geometric object. If you want, you can look up Kummer's surface um, on Google, and you see kind of pictures that will melt your brain. Anyway, so this is all in higher dimension, projective three-dimensional space, and so you have these complicated things, but you have but the configuration of these nodes and these conics, nodes and conics, the way they intersect, it's actually quite easy to write down. So somebody in 1981, I think it was, I don't remember the name of the author. Somebody found this. So what you do is you take your 16 points, which are your 16 conics, if you want, or your 16 nodes. It doesn't matter. They're interchangeable. So you want lines. You want blocks, right? You want six. You want to take sets of size 6. You want to collect subsets of the set for all numbers from A, B, C, D, E, F, G, H, L, M, N, O, P. So that's your 16 symbols. You want to collect them into sets of 6 each, right? So I just put them in any order. It doesn't matter. You just have to put them all in a block. Sorry, you want to put them all in a 4x4 grid. And what you do is you want 16 blocks. So how do you pick your 16 blocks? You take any one of these blocks. So here I've chosen N to be highlighted. And then you take all the other points. Don't take N, but take all the other points that are in the same row and in the same column as N. So you have C, O, H, L, M, E. So you have, for each of these 16 squares, you can pick that, and you can take all of the ones that are on the same row or on the same column with it, and you get 16 blocks. So you got 16 points and 16 blocks. Each block is in 6 different. Each block contains 6 different points, because there's 3 on the same row and 3 more on the same column, and each point is in 6 blocks, because there are 3. It will be in the block of the 3 on the same row and 3 of the same column, and any 2 blocks will intersect in 2 points, and any 2 points will be in exactly 2 blocks. So it's a very symmetrical system. So what you have there is what you call a symmetric design. There's other things also that come from algebraic geometry. So Gino Fano was trying to study projective geometry purely in an axiomatic way, and he came up with something called the 7-point projective plane, which is also known as the Fano plane. It came to have his name, but again, Kirkman had discovered the triple system, the incidence structure. So basically, not the picture as such, but if you actually gave them all names, and if you took everything that was connected by a line into a block, so you get 7 different lines, so you get 7 different blocks of 3 made out of 7 points, and every point has 7 blocks, and any 2 intersect in exactly 1. You get that system. That Kirkman had discovered that before him as well. So, and again, he didn't get any credit. Poor Kirkman. Okay, so this is what we call a finite projective plane. So it satisfies it's a finite set which satisfies all the axioms of projective geometry, which is not something that you think of as a finite thing. You generally think of projective geometry as an infinite thing, but it depends on what field you're doing it over, and in this case, you're doing it on a finite field. But if you just write down those axioms for a set of points, you have a finite projective plane. Okay, so here, and then somebody clever came up with an easy way of remembering this, which is you just take the letters. If you read out the sentence, yeah, why try her raw wet hat, which is a weird sentence, but if you look at it, there are 7 letters that go into it. Every letter is in exactly 3 words, and any 2 words will have exactly 1 word in common. So that's an English sentence. That's a finite projective plane. I mean, that's kind of cool. Right, so there's all these combinatorial designs being done, and then also, so statisticians were thinking about it because they wanted to not waste too many resources when they were doing their statistical experiments. So they wanted some nice configurations where you could apply treatments selectively, so that different combinations of treatments would be applied to different patients or different agricultural lands and stuff like that. So that's so statisticians were thinking about these things, and they came across these same configurations, and they called them block designs. Okay, so I call them block designs because I'm a graduate of the Indian Statistical Institute, where people like Bose and Rai Chowdhury and people like that did like Bose did a lot of work on designs. So they called it designs. My professors called them designs, so I call them designs as well. Okay. And nowadays most people call them design, so it's a part of applied statistics almost now, but it's also part of mathematics. So by this stage, combinatorics is very purely mathematical. It shows up in all these geometric situations, but it is also uh, it's also very applied. So people are now using them for tournament scheduling or scheduling classes, for lotteries, for chemistry, for biology, for design and analysis of algorithms, for networking, testing. So if you want to do testing on groups of subjects, cryptography, it's everywhere, right? Designs are extremely useful things now. So, okay, we said what designs are, kind of. I glossed over the definition, but you can always look it up, or I can send you the slides later. So there's a question of, okay, right, so you define these things, but do they exist? Yes, so a mathematician at Oxford called Peter Kiefish recently said that for all feasible parameters. So you can't have like designs with any number of numbers. They have to divide into each other evenly and so on. Right, so the number of blocks will have to separate out everything, and you don't have a remainder left over or something like that. So you can't separate 10 objects into blocks of size 4 because you'll have 2 left over. So that's so there are some parameters are feasible. There are some very very basic conditions for that, and for that and with very small exceptions, with small numbers you may not always be able to do it. But if so here I call them tvk lambda designs, right? So for any k and lambda, if v is big enough, the total number of points is big enough, you could make a design, right? So that was solved using probabilistic combinatorics. That's another area of combinatorics altogether. And so he used probabilistic methods, and he found that you basically always have designs. Okay, right. That's a result that makes most people very happy, and I absolutely think it's amazing. But for me, designs are all about symmetry, and most designs don't have any symmetries at all. So what I am interested in is algebraic combinatorics of designs. So designs that are symmetrical. So if we go back, or maybe if you remember back to the slides that we saw earlier, all those designs are quite symmetric in nature, right? I mean, this way you kind of twist them around, you can pick them up with your hands and you can kind of move them around. They still look the same. There are, I mean, whatever you personally recognize or in your subconsciously recognize the symmetry, it is there. You look at them and they make you just that little bit happier, I hope. Anyway. So they are symmetrical, right? And but the best way of studying the symmetries of these things is through algebraic combinatorics. So again, all these, so as Krishnachandran said earlier, it's not true that like there are no branches of mathematics. Everything is mathematics, and even if you kind of put them into different bins, they're always helping each other and kind of providing ideas from one to another, and it's all rather I mean they kind of exist in a certain synergy. So basically you have linear algebraic methods, you have what you call them, you have matrices, and you using matrices you could do things like look at the spectrum of a matrix, and you could use that to write down the adjacency matrix of a graph, and you can use that to write the graph spectrum. You could look at linear spaces over finite fields, and you could do the linear algebra on that, and you get coding theory. So there are all these methods from linear algebra that we use in combinatorics all the time. Also, you have algebraic and number theoretic invariance, where you have like things like what's it called, polynomials, about graph coloring polynomials, not polynomials, things like that, and you use that in order to see whether combinatorial structures exist or not, because you check whether the invariants are satisfied. You have commutative algebraic methods, which have been used very to great effect to study combinatorial structures by people like Richard Stanley. And my favorite bit, which is when you use permutation groups, right, to permutation groups to study structure preserving symmetries. Now, what's that? So basically, say you have something like a design, you have all the points on the design, and then you look at the symmetry group, which I hope everybody knows what that is. If you've done some group theory, it's basically all the ways you can swap them around with each other. And then you look at the symmetric groups that also preserve the blocks. Okay, so I don't want to write that down. I'm sure everybody's just had lunch and you're probably already asleep. So let's not do any calculations in this talk. Anyway, so you look at structure preserving symmetries, which are quite beautiful, and then there's also other bits of algebraic combinatorics, like things like studying Young's tableaux, association schemes, metroids, which are all generalizations of algebraic concepts like linear independence and so on. So this is Josephine Yu. She studies combinatorics, and she works in metroids, and she says combinatorics is the art and science of distilling a complex mathematical structure into simple attributes and developing from this a deeper understanding of the original structure. So studying, for example, invariants, studying, for example, there was something on my, I forgot. Anyway, so you get like Bird said, right? If you look at the intrinsic properties, so you study the graphs based on that. You take a real life situation and you turn it into a graph, and then you look at the properties of the graph and use that to understand the real life situation, like who's friends with whom on Facebook and stuff like that. Right. Okay. So that's I think that's a very nice description of combinatorics. Right. So I have about 4 minutes, and I thought I should give you a very quick introduction on what I do as a mathematician. So I work somewhere between combinatorics and geometry. I can do combinatorics. Can do geometry with great difficulty. So what I do is, so you look at a space like a circle, and I don't quite like the fact that a circle is given by an equation x squared plus y squared equals r squared. So that's and also nowadays you have computers, so computers want to computers don't understand anything x squared plus y squared plus r squared. But if you take a computer and you tell them it is the area bounded by 3 points and all the points are connected to each other, you could kind of replace things like equations with a set system. So that's what I study, and that was how algebraic topology came about initially as well. Anyway, so I study things called simplicial complexes, and simplicial complexes are models for sort of manifolds. So for example, if you take a sphere and you could kind of put triangles on it and you join them up in a nice way and you get nice triangles, right? So I study spaces like projective space, where you translate the combinatorial conditions into geometric restrictions, and then and then I wanted to see, oh, what's the smallest you can make. So I don't know if you can see my my feed. Here is a tetrahedron. For me, this is like the smallest model you can make of a sphere, by where everything is like flat and bounded by lines, and the lines are all glued together nicely. So okay, but if I want to make a projective space, for example, what I will do, I can't a project. Okay, what I will do is I will think about, okay, what's a projective plane? It's the antipodal quotient of the sphere. What does that mean? I take a sphere and I take any point and I take the point directly opposite it through the center, and then I kind of glue them together. So here is the times where, like, this is not something that exists in three dimensions. You can't really draw a picture, but what you can do is you could say, okay, I take a flat disk and I take the boundary of that disk and I pick it up and I kind of twist it and glue it back together like this. That's a projective plane, right? If you can't see it, don't worry about it. I can't see it in my mind either. Okay, so for example, so if I want to say, okay, so instead of like a continuous smooth projective plane, I want to write it in terms of little flat triangles that can be glued together nicely and described in terms of finite sets, I have like a picture like this. So, and this will give you, so basically if I write down all the blocks, so this is now coming back to the language of design theory, this is now a set of 6 points, and every triangle is a block of size 3. And any two blocks intersect in, any block has 3 points, any point is in 5 blocks, and any block, and yeah, any two blocks intersect in either 3 or in 2, which is an edge, or 1, which is 0 point. So this is an isometric structure, and this is and every time you swap around the 1, 2, 3, 5, and 6, you get different what do you call them? You get different labelings of the same space, and this has and it has 120 structure preserving symmetries. Okay, so that's symmetry makes me happy, so I'm quite happy to do that, to look at that. Sorry. Oh, I want to, okay, and that is also when I said it's an antipodal quotient of a sphere. So here's my favorite icosahedron, and this is a platonic solid. We saw a picture of it before, and this, if you kind of quotient out by the antipodal map, as we say, or if you kind of flatten it by by kind of mentally joining everything to its opposite point. That's the thing. Okay, right, I'm out of time, so I'm going to very quickly run through my next slide. So we do this in higher dimensions, and you find all these you basically, like, it's kind of very, very cool what happened in the case of all of us working in projective space, which is that Frank Lutz is a German mathematician, and he kind of used a geometric idea where he started off with a big triangulation of projective space, used computer searches, so you kind of just mess around with it and you break all its symmetries, but you just keep trying and make it smaller and smaller, and he found a space which has actually 720 symmetries, even though you have no symmetries as you go along. Suddenly, when you come up to the minimal object, you kind of suddenly find a symmetry, right? So sorry, okay, so and what I like to do is I like to use kind of nice symmetric objects that we already know, like groups and designs and things like that, and I want to kind of say, okay, right, now if that is the basic configuration inside of it, how do I kind of extend that out and make it into a geometric object? Like, what should I pick so that all these various conditions are satisfied? The combinatorial symmetry and also the geometric structure are satisfied. So you kind of so whatever Lutz found by computer search, I found with symmetries, and it's well, basically I took this object and I worked back from it, and I was like, oh, these are the symmetries, so now I know exactly what the thing does. Okay, so you kind of work on that. And then suddenly I was looking at the object a little bit more, because you never actually stop thinking about any of your problems, even if you think you solved them. I was like, oh, wait. So this is the geometry, and this is how it works. And then I'm like, but this thing is a lot more symmetric than I thought. This is actually contain, and I was able to establish connections of that with various other geometric objects that are well known. So here is a picture of the outer automorphism of Sim6. Let's not worry about that, and I'm 2 minutes over time. And here is a picture from my paper on the projective space. And this is like a nice template. You could look at it and write down the combinatorial object known as the nicest biplane. And if you kind of think about it a little bit more, you come up with something called the Vidya sign on 22 points, which is kind of quite famous in mathematics. Right, okay, so that's why this quote kind of spoke to me. One starts out in life trying to do mathematics and winds up doing combinatorics. Okay, right. So I like to do combinatorics. When I was an undergraduate, my professors would be like, combinatorics is hard. And I would say, well, that's what makes it fun. Okay. Well, so all the quotes I used on this page, they were all collected quotes on combinatorics by Igor Pak. So that's the link. If you want the slides later, you can click through there. And I want to leave you with a thought by the analyst Leonard Carlson, who solved very, very hard and difficult and important problems in Fourier series, where he says that every hard problem in mathematics has something to do with combinatorics. So I hope that has made you interested in combinatorics to some extent. And here are some books if you want to get started on sort of the kind of combinatorics that explore structures and symmetries. Okay, right. Well, and also there's a lot of combinatorics and symmetry in nature. This is the Giant's Causeway from Ireland. And thank you, and everybody stay safe. Hopefully we will all meet again soon in real life. Thank you.
Okay. Thank you.
I want
Sonia.
to stop presenting. Stop.
Okay.
Okay, thank you. Thank you, Krishnachandran, sir.
Yeah, okay. Anybody wants to ask any questions? Somebody will be having doubts? Can somebody ask how she was attracted to combinatorics? How you came to?
Why I enjoy combinatorics?
Not why.
Because
how?
it's difficult and it's, you know. But when you solve a problem, you know you really solved a problem. It's not yeah, so, and it's beautiful.
Because it's difficult.
Okay, any questions from the audience? Okay, it was really, see the energy, the way you presented it, some historical. My daughter-in-law is an Ayurveda doctor. I tell her you were talking about Thrissur Samhita. Okay,
Thanks everybody for coming. I hope I didn't keep you too late.
Okay. So it was presented very well. Thank you very much. On behalf of the organizing committee also, I would say thank you. You made the evening very, very lively. Very lively. Thank you. Yes.
KVM sir is waving to you, Sonia.
Hi, KVM sir.
Are you on the bed or what? Did she put you to sleep?
One thing I can do is I can keep people awake. So yeah.
It was one single shot right from the beginning with no.
Did I go off like an arrow?
I just went. Okay.
Okay. Thank you, mother.
I can say that I understood you better rather than reading your thesis. I didn't understand much when I read your thesis, but then I understood whatever you are presenting right now. Perhaps because it's more or less not all that deep.
It's deep, but I didn't. Well, the material is deep, but I didn't go deeply into it.
I mean, your presentation, you might not have gone deeper because, it was, perhaps you were touching the superficial portions. It was very well understood. Okay? And
thank you, ma'am.
Though a mother, I think I learned from you as to how to present things. Okay. So perhaps we are calling it a day. So stay safe, okay?
Vidya, please.
Yes, sir. So thank you, Dr. Sonia Balagopalan, for having delivered a very informative talk. It is said that a good listener makes a good speaker. I think that is what we saw just now. The patience that you took to listen to the talk of Professor Dr. V N Krishnachandran was well displayed in your powerful presentation. It was really interesting listening to you. You're a very passionate learner as well as a teacher, just like your mom. So thank you, Dr. Sonia Balagopalan. We also thank our very own conference chairman, Dr. V N Krishnachandran, for having taken time to chair the session after a very long session of your own. Thanks to all the participants for your patient hearing. Today's session comes to an end. We request all participants to join at the same venue tomorrow at 9:30 for the fourth set of invited talks. The feedback link has been already shared in the chat box. You may please fill the feedback forms. So thanks to all participants for your active participation. Thank you and have a nice day. Thank you.
So we too thank you for a very interesting day. Yeah. And it was an interesting day, started by all the presentations. Thank you. Let's hope all the participants enjoy. Yeah.
Yes.
Thank you. Thank you, Sonia.
Thank you. Bye.
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 So thank you to the organizers for giving me a chance for me to see my daughter again for one full hour.
Thank you, ma'am. Thank you.
In fact, this is the first time that my husband came and listened all the while. Yeah,
a different experience the pandemic is giving.
Father-daughter relationship. Okay, then thank you. Bye to all of you.
Okay. Thank you.